to give a few words about the presentation that Andrea and Francisco will share today, as well as of the content, and a few words about the expertise of Francisco and Andrea. So the webinar will focus on innovative strategies for the repurposing of composite materials at their end of life. And this will be today we will discuss actually sustainable reuse solutions for high performance composites, the applications for repurposed materials in various industries, and the role of the repurposing in promoting a circular economy. Dr. Francisco Lahuerta received his PhD from TU Delft and his engineering industrial degree from University of Zaragoza. Currently, he's working in the Innova in Zaragoza, in Spain, as a research scientist, and he has contributed actively to industrial and funded projects related to lightweighting, optimization, data science, composite manufacturing and recycling, modeling, mechanical testing, and structural health monitoring. Dr. Andreia Araujo, that she will present the second part of the presentation, is an advanced materials coordinator at INEGI, and she has extensively worked on the development of epoxy formulations containing different types and loads of carbon-based nanoparticles, and on the production of pre-impregnated materials and carbon fiber reinforced polymers with improved properties. So today, our speakers will discuss the reuse and repurposing of the end-of-life high-performance composite parts. So the floor is yours. Please, Francisco, you may start. Thank you very much.
Okay, thank you very much, and good morning. My name is Francisco, and I'm a researcher in ITA, and in collaboration with Andrea Araujo from INEGI, we are going to present part of the work that has been carried out to the moment in relation with reuse and repurpose of end-of-life high-performance composite as part of the EuReComp project. The EuReComp project is based in the R6 strategy, which includes the different circular pathways for the management of end-of-life parts, including reuse, repair, refurbish, remanufacture, repurpose, and recycling. This presentation, the part that I'm going to explain, belongs to the reuse and repair, and Andrea will focus on the repurpose pathways. As we can see in this slide, the lifespan of a wind turbine blades are usually manufactured with composites and is around 20 to 25 years. This is mainly related with the fatigue limit of composite materials and the sectoral design guidelines. On the contrary, that steel composite materials don't have a fatigue limit. Therefore, eventually, in some moment of operation, composite might fail due to damage, accumulation, and the wear. However, there exists some sectorial normative where it is allowed to extend the life of a wind turbine blade for around 10 years, depending on the state of the loading conditions of the wind turbine. This applies to almost all the wind turbine blades. However, wind turbine blades require to fulfill a series of conditions that are given by the sectorial normative described in the slide, including some DNV-GL guidelines. In this slide, as a brief breakdown of the life extension process of a wind turbine blade, is described in this slide. Initially, when wind turbine blade lifespan of 20 to 25 years is ending, it is required to be collected a large amount of data, which is related to the test site information, historical data, the maintenance reports, the data of the system, the site permissions, and eventually, if there is some conditioning monitoring system in place, the data from the conditioning monitoring. With all this information and the load modeling, it is possible to analyze the remaining useful life of the wind turbine and all the structural components. Also, it is carrying out some end-of-life inspections, assessing the conditions of the wind turbine blades.
В Роттердамі не офіс, сама, якщо вас
Sorry?
цікавить, що сама логістика.
Oh, sorry. Okay, we will continue. Moreover, it is required the report and the certification, which is documenting and certifying all these findings and implementations applied to the conditioning monitoring techniques, the optimization of the fleet, of the wind turbines, the maintenance, and the necessary repairs that might be needed. When wind turbine blade life is extended, the loop close requires some continuous monitoring and data collection to assess the process which is ongoing and in order to be verified all this data. In the project, we have only focused in the repair parts and the parts of the assessing of the structural component with wind turbine blade by analyzing the residual useful life, which is work that is ongoing at this moment. In relation with the repair techniques that is shown in this slide, there are repair techniques related with the protection and erosion of the wind turbine blades. And these repair techniques are related with the use of filler or coating tapes outboard of the wind turbine blade, where the highest speed of the wind turbine can be found. Moreover, wind turbine blades might be equipped with some metallic shields or shields manufacturing of composite materials outboard at the tip, where you might find the highest tip speeds of the wind. In relation with the structural repair, there are different kinds of options related with the repair of the structural parts, which are patches and scarves, and in this one is mainly related with two different manufacturing techniques, which is the soft patches and the hard patches. In both cases, initially it is required to remove all the damaged region, and the layup of after the layup of the repair material is applied, which can be pre-cured or not, or it can be dry. And in both cases, it is required the preparation of the final surface once all the curing and the consolidation process has been carried out. In the EuReComp project, we are evaluating the repairing techniques using 3D additive manufactured printed cold plates tools. This is carried out in collaboration with BioG 3D for the 3D printing of the cold plates, which also is one of the project partners. The work is based on evaluating the end of the surface that we obtain with the use of the cold plates, which has been manufactured by 3D additive manufacturing techniques, and where the main benefits of these techniques that we foresee is that it's possible to avoid secondary finishing, like the grinding, and improving the superficial tolerance of the repairs. Potentially, it's possible to use 3D printed parts, which has been tailored for the warping surface that normally you can find in the wind turbine blades, and it's possible to carry out this work with a relatively good geometrical tolerances, and this can be applied to repairs that are performed by drones, because it can avoid the use of the by the drones, because it can avoid the use of the vacuum bag and all the vacuum procedure. And well, at this moment, some demonstration trials with the 3D printed cold plates has been carried out, and where good surface tolerance are possible, and it's possible to produce trial patches. The project is moving forward. It's not finished at this moment yet, and we are working on a second demonstration with a 3D printed cold plate that will be applied on a real surface of a wind turbine blade that was provided in the project. The main steps of this process are shown in this slide, and these are can be summarized and initially in the identification of the damages. Later, the definition of the required specifications. We also need to obtain the CAD model of the surface, which can be carried out with a 3D camera. And later, with all this information and the CAD, the cold plate can be 3D printed, which this work is carried out by BioG 3D, and later with the cold plate we can apply the patches using this cold plate in a final consolidation process with a thermal blanket or some infusion. And so yeah, here it ends. And what to do when life extension is not possible? Well, this is something that will be answered, will be explained by our colleague Andreia Araujo. So should I stop sharing? Yeah. Okay.
Yes, please. Thank you, Francisco. I will start sharing my screen now, and I will continue with this presentation. Are you seeing it in presentation mode?
Yes.
In full screen? I mean, yeah, awesome. Yes. So as Francisco mentioned, our goal at INEGI and in collaboration with other partners is to look into other art strategies. And in this case, what to do when life extension is not possible, and more specifically, how can we repurpose end-of-life wind turbine blades to make sure we are not contributing to a huge amount of waste being just left on our continent. There are several study cases or implemented cases, let's say, where end-of-life wind turbine blades have been redesigned for a new application. We can start by the Wicado playground, where 5 30-meter-long blades were cutted and used as a safe place for children to play. The second case study is the Willemsplein public seating. This is in a square in Rotterdam, where they used 9 6-meter-long wind turbine blades to make public sittings. On the right side, we have a bus shelter converted from 3 pieces of a 30-meter-long blade. And on the bottom, we have a pedestrian bridge where 2 8.5-meter-long blades were used as the side girders for a bridge. Last but not least, we also have, let's say, different case study. And this is a conceptual architectural housing for, or thought for underdeveloped countries, where different sections and different parts of the end-of-life blades could be used for the constructions of houses. So striped panels could be used as doors, window frames, panels, facades. The top and bottom airfoils of the blades could be used as the roof frames for the houses, and other curved parts also for the roof. And a root section of the blade could be used as an elevated foundation for the house, for instance, to prevent damages during floodings. These are some studies or some case studies that we can find easily on the internet, but there are many more, and there's increasing interest in this route of the art strategies. In the EuReComp project, we did an extensive search, and we kind of divided the approaches into 4 areas. The first one was on ideas on how to use a complete wind turbine blade for high-loaded applications. The second segment, let's say, was again how to use a complete blade, but for low-loaded structures. Then the third approach was high-loaded segmented structures, and the fourth, low-loaded complete segmented structures. On the right, there are some images, some of the case studies presented in the previous slides, and others that were not. And based on this search, we ended up with the idea on a repurposed demonstrator to be developed during this project, which was a floating PV structure. And we started in collaboration with HTWK to design and develop a small-scale demo case. This would support one PV panel. And the idea for this first approach was to have an initial proof of concept for the final application, develop a methodology for closing the ends of the wind turbine blade segment, because of course, if we want this to float, we have to make sure no water enters in the structure and weighs it down. Of course, evaluate the floatability of the demo, and then other features. I wanted to point out that this small-scale demo, in this small-scale demo, there was the use of aluminum profiles as the supporting structure for the solar panels. And I can tell you that this demo case was successfully constructed by HTWK, and here is an image of the demo floating in the water. So, successful approach for this demo case. With this in mind, we started developing the large-scale demo. In here, we decided to use 2 segments of wind turbine blades with bigger dimensions to make sure we could add more more PV panels. In this case, we thought 4 was a good idea, and in this way, we could manage to have a big enough demonstrator, but not too big that couldn't be produced and transported by us. In this case, to make sure we were further increasing the repurposing and reusing of different parts of the wind turbine blades, we decided to replace the aluminum profiles by glass fiber reinforced polymer beams from the spar caps of the wind turbine blades also. And this way we could make sure that at least most of the components of this demo came from end-of-life materials. After designing this demo, we had to make a huge effort trying to collect information on accurate dimensions and structures of blades. We have to investigate the best approach to connect two segments, making sure that all the screws and other things needed to combine these two parts were inserted in a robust part of the segmented blade. And afterwards, we managed to find the right sections, thanks to a Portuguese winterbind blade dismantler called Ventos Metódicos. And with their support, we cut it. We obtained 3 10-meter long winterbind blade sections, all from the same winterbind, all with the same size. From the 10-meter long sections, we studied fully one. We managed to recover all the accurate dimensions and so on from that. And we use all that information to design and develop our demo case. We also cutted the GFRP beams from the spar caps to be used as a supporting structure for the final PV panels. And then we did all the necessary work to calculate center of mass, to make estimations on floatability, and decide on how to combine all the different elements of this demonstrator. And here's just a GIF representation on how we started or how we decided to construct the demo. And at the moment, this demo is under construction. I would like to save the final images for later on, but I urge you to follow us on social media and make sure you check the final demo, the construction. I would also like to mention that for this demo, we are planning on testing its floatability, not in open waters, but in let's say research pool, where we will also conduct a test under the influence of waves to make sure we can have a better understanding on how it would react in open air conditions. In any case, this demo is under construction. We are really happy with the developments so far, and we'll be eager to show you the final image once everything is ready. Once again, more information and updates can be found on the project website and will be shared for sure on the social media. And I would like to thank you all for watching this webinar series, and also me and Francisco, we will be glad to answer any of your questions. Thank you.
Thank you very much, Francisco and Andrea, for your descriptive presentation. We are open to questions from the audience. You can raise your hand, write in the chat, or just ask a question that you may have for the speakers. Okay. Yes, Maria, please.
Yes, hello. Can you hear me?
Yes.
Andrea? Yes. So my question is for you for the repurposing. So do you have to do some in order to repurpose the wind turbine blades? Do you have to repair the parts in some kind of way in order to, for example, use it as the floating for the floating that you showed?
Okay, so basically that depends on how well the blades were handled during dismantling. We've seen a lot of damages that occur during the dismantling process, and in those cases, yes, some repairs might be needed to make sure no water gets inside of the demo. Otherwise, as I mentioned, all the structure will go down in the water. And that's why the sealing of the ends is so important, and also the type of screws and the way the screws are inserted in the smaller segments are important. Of course, we try to select segments that show no damages, but in case we find them, we need to do some sort of repairing, for instance, by adding extra glass fiber fabric and epoxy resin or other type of sealant to it.
And now for Francisco, my questions now go to Francisco. How effective is the repairing on the wind turbine blades?
At this moment, we are still working on the second demo, and once the demo is carried out, we will evaluate the repair mechanically. So potentially it can be effective, but it's still an open topic.
And what kind of test are you going to do for to evaluate the repurpose? The use.
At this moment is on definition, but probably we will slide or cut like coupons from the repair, including part of the wind turbine, and we will test these coupons. I don't know yet if on flexion or traction, so we can make a kind of mechanical assessment of the repair. Did that answer the question?
Yes, thank you.
Oh.
If I may continue the question that Maria asked to you, Francisco, can you consider what are the cost implications for industries to adopt these practices, and especially the repairing practices, which is something novel for our project?
At this moment, we have or we are collaborating, and we have made like an LCA assessment with Nicolene, and there we have provided some of the information, and but in terms of cost, we haven't carried out, but it can be included as part of the work package. Yes.
Okay, and since you mentioned about LCA, this question comes to both of you. Have you considered the long-term environmental benefits of implementing either the reuse or repairing strategies? Can you consider which will be more beneficial for an end-of-life management strategy in terms of environmental benefits?
Okay, maybe I can start this one. So basically, when we're talking about composite materials based on thermoset matrices, as you know, it's different. A thermoset matrix is different from a thermoplastic one, where we can just reprocess it and construct a new parts based on it. This is not possible for the materials used on wind turbine blades. So with the repurposing pathway, we are basically extending the life, let's say, of these materials instead of just having to put them on the ground or find other solutions. So based on the currently used approaches, this is more sustainable. But of course, at the end of life of these new products, the same considerations will need to be made again. So can this at its end of life be again repurposed? And if yes, we can once again extend the life of these materials. Otherwise, they would have to follow other approaches like recycling or so on. So I would say we are in fact improving its sustainability, but for a certain period of time.
Okay, thank you for the answer, from the reply. There is also an answer, question from the audience. And the question is, how do you reassure that the reused new product does not affect negatively the end users in a matter of health safety?
Other reuse. In the case, for example, of the repair, one of the benefits is that it requires less. On one hand, it requires less work on the finishing of the surface. So one of the benefits from the point of view of the LCA and also from the health safety is that you avoid a lot of grinding and powder. And that is also is a good point in terms of health safety, and also if potentially it can be used with the guns, and this also reduce the implication of labor and in harsh conditions like climbing to a wind turbine to make repairs. So that is also some of the benefit in terms of health safety, that you are avoiding the risk.
Thank you, Francisco, for your answer. Is there any other question from the audience? Okay. So may I ask a next question to both of you, or probably this is more close to Andreia. There's also Philippe. I will give the floor first to Philippe just from HWK, and afterwards I will ask from our side.
Yes, thank you very much, Kate. So thank you from my side for this both very interesting presentations. So my question is in the direction to Andreia. So Bom dia. So one big challenge within this repurpose strategy is to scale up the material to be processed within repurposed applications. So more or less is the question if you believe if this application of this PBV floating demonstrator is able to be scaled up to a high amount of material, basically.
Thank you, Philip, for your question. So basically, we decided to go for a large-scale demo, but not that large if we consider the size of the end-of-life wind turbine blades at the moment. So I would say that the ideal would be to further scale this up and use the full blade, or use full blades for the construction of this type of floating structures. This way, the production and scale up of this type of materials would be easier than to do it the way we did by trying to fit or trying to find the best segments from which part of the blade we would cut to get the right segments for the production of the demo. Another thing, of course, is that as a research institute, we have a certain amount of capabilities for the construction of this type of demos. And I would say that for a specialized industrial partner, having done the first, I would say, prototype, scaling it up with the right tools would be feasible. I think, at least.
Okay, thank you very much. May I add, I also liked the idea of using the spark caps as the frame construction of the solar panels, because this spark cap material is basically more or less always the same from wind turbine blade, always the same within different wind turbine blade types. So that's why I believe that there's also a lot of potential material coming from the spark caps. Yeah, so thank you very much.
Yeah, sure. I was thinking more about the scale up of the demo itself, but I would say that if we consider other type of possible products from the end-of-life blades, beams from the spark caps, I would say are quite scalable production and probably quite useful, for instance, for the construction sector or other industries. And we've seen a lot of ideas coming out from Ventos Metódicos, where they are applying some of these materials, I would say, in their daily life, in their building, and also finding new products even for agriculture purposes and so on. So there's a lot of potential if we look into smaller parts from the blades.
So I think that your last reply can give me the floor to ask you our last question for today, which is the regulatory challenges that probably you will face if you want to facilitate the reuse and the repurposing of composite parts in such applications. And if the standardization is something that will ensure the quality and safety of the repurposed materials, or something that will give obstacles to these repurposing routes.
In terms of safety, well, this is similar to the previous answer. From the point of view of health and safety, improving the repair methodologies, you also reduce the risk, and so all the risk assessments will be simplified in the sense that you produce less powder, you need less grinding, and also if potentially it can be used with the guns, you are also reducing the risk of the labor that might be required on high heights when you are climbing to a wind turbine or this kind of sense. So yes, potentially it can be beneficial from the point of view of increasing the safety. Yeah.
The standardization. And as for the regulatory challenges that probably we can face in such a repurposing activity?
Repurposing. Okay, so basically, some challenges that we are facing, depending on the application that we are looking for, is the lack of standards and information on how to safely reuse or use these CFRP fiber reinforced polymer parts. I would say that having some sort of standards assessing the properties of the materials would give more confidence to end users to safely take advantage of these end-of-life parts and components. From a perspective of circularity, as we all know, sometimes it's way more expensive to recycle, repurposed end-of-life materials than to just go get the raw materials and construct a new part. But I would say that regulamentations would play a key role in this to make sure that the sustainability and circularity is taken into account on to decide which path to follow. And this would be advantageous to make sure these end-of-life parts are receiving a new life. In terms of reuse, I would say that really depends on the application sector, because if you look into the aerospace, aeronautic sectors, there are strict rules guiding the reuse or the not reuse of parts, and maybe we are in need of some sort of testing or standards to test these end-of-life parts and assess if they are in fact good to reuse or if they have real damages, because composite materials have a long durability, and I would say that in some cases maybe we could just extend the lifespan of the components and parts.
Thank you very much, Andreia. And there is also a question in the chat that I guess it goes for the demonstrator that you selected to present. And the question is, how will this construction affect marine life in general? If we will have any effect on the marine life when we are trying to make this type of floating PV panel?
Good question. Actually, for this floating demo, we were looking more into not salt waters with less influence of big waves, for instance. So we were looking more into lakes or other water courses, because for sure, if we were considering the ocean, the construction of the demo would have to, or the design of the demo would have to be a bit different. In any case, for marine systems, we have other types of floating platforms already applied. So I would have to do a bit of research on the impact of those platforms and try to make a connection to here. In any case, if it's just above the surface, I wouldn't expect a huge impact. In fact, we had a previous project developing a floating, let's say, island for waters in Portugal. And in that case, or kind of reservoir water to also be used for agriculture. And we had a quite good impact overall in containing the water in the reservoir, because the floating structure avoided water evaporation. So that was a good consequence of having it.
Okay, thank you for your answers. I don't know if there are other questions. Otherwise, we can close our session today. With this, I'd like to wish you all Merry Christmas and to enjoy your holidays. For our audience and those that participate in today's webinar, please stay tuned, since in the mid of February we will have the next EuReComp webinar. This will be delivered by our partner IMEN and be related to the quality checking of end-of-life composite parts. A few questions today were also related to these activities. So please stay tuned, and you can follow also the rest EuReComp webinars. Thank you very much, Andreia and Francisco, for your today's presentation. Okay, and hope to see you again all in our next webinar series. Thank you very much.
Okay,
See you soon.
thank you very much.